It's like a 10-point word. All right. So anybody want to guess who this guy is?
We get a hint. Some old crusty European guy. Old crusty.
I mean, that's all of them. So.
Does that make it wrong?
It's not wrong. It's just not specific enough.
Fair enough.
It's like if you ask me what's on the test and I'm like
Physics. Yeah. That makes sense.
That's correct. It's not gonna help you. Guess who's so we have these equations we keep talking about.
Yes. Is that Henry Maxwell?
Maxwell. Oh. Yeah. This is he looks a little older than the other photo that we use, but more beardy.
More beardy. It just looks like the hair on his head melted down.
yeah. Well, that's what happens with age.
Is that how it works?
Yeah.
Gravity takes
and
over.
then eventually it just hits chest and back. And
to a lot of men. Yeah, like the other physics professor, our other like full-time guy, is completely bald. And he's just given up and he started, shaving it. And he used to teach high school, and his high school students, I guess it's like Teacher Appreciation Week, which only exists in K through 12 because they pay us a reasonable wage. You notice if there's Appreciation Week for your job, it's probably because they don't pay you enough, right? Like,
I've never heard of McDonald's employee appreciation.
There's no like CEO appreciation week, or like there's actually not even like there's a nurses appreciation week. There's not a doctor appreciation week. There's no lawyer appreciation week. Like people whose jobs make real wages don't get an appreciation week.
Damn.
So be wary if like secretaries appreciate. These are people that don't get paid enough, and other people crap on all the time. So yeah.
EMS, bro.
There should be a fast food worker appreciation week.
There is. They don't get paid.
There isn't, but there should be because it qualifies. But they're also normally traditionally female jobs too. So we were like, we're not going to pay you an equal wage, but we will give you a day or a week where we bring you a card. So that's pretty good, right?
And then we'll find out.
Anyway, side note on social politics. So this is Maxwell, and we've talked about his equations a lot, okay? And remember, what are they? One of them's on this next test.
Shit.
Going all the way back to the beginning, right?
Okay.
We have Gauss's law.
There we go.
And there's two of those, because there's one for electric field.
That seems like such a long time ago.
Okay, and there's one for magnetic field, which is less exciting. Doesn't come up as much. Okay.
Mm-hmm.
So this would be electric flux. This is magnetic flux. Alright? So Gauss's law for electricity, electric Gauss's law, magnetic Gauss's law. Alright, and then we have Ampere and Faraday. Right? So Ampere's law is V dot ds. This one's on the test. Equal to mu naught I through. Okay. And then there's actually a second part to this that we haven't talked about. And I'm just going to write it on there. Okay. So that's Ampere. And then we also have Faraday. And that one gives us
What does that say? Mu naught I.
It's mu naught d.
this.
Electric flux over dt.
Okay. So these are Maxwell's equations, and this is written in integral form. You can also write them in differential form. You've taken vector calculus. That will make more sense. But basically, anytime you have these kinds of surface integrals, you can use Gauss's What do these things say?
Through.
Like, what does it mean to have this double integral? What are we calculating?
Enclosed surface.
It's an enclosed surface. Okay, what are we calculating inside this enclosed surface or through this enclosed surface?
Flux.
Electric field inside.
Flux, right? This says we're calculating the electric flux through a closed surface. Okay? This says we're calculating the magnetic flux through a closed surface. So this says the electric flux through a closed surface is going to exist, right? You're going to have a non-zero flux if there's a charge inside the closed surface. Okay, that's Q inside. Right? This is just a constant. But these constants end up being really important too, because remember, what did we learn from these constants?
Permeability.
Depends on the material.
Speed of light, right?
1 over square root.
And we can go through the whole derivation to show you where that equation comes from.
Interesting.
I think you already did it.
We didn't. We referenced it, but we'll save some time. We can do it. So this says if you have flux through a closed surface, charge can give you a net flux through a closed surface, but magnetic dipoles can't, because inherently the electric field lines, the vector field from charge, can diverge or converge on a point, whereas the field lines for magnetism, magnetic field lines, they don't converge ever. They're always loops. Okay? Now, electric field lines can be divergent and convergent. They can be spurs, but they can also be loops. Magnetic field lines can only be loops. So there's a little bit of an asymmetry between electricity and magnetism. As you can see, right, for every version with the electric field, you have a version with the magnetic field, right? This matches this matches this. But what happens over here is a little bit different. So we find that, when we look at how physics works at a fundamental level, things are always a little bit asymmetric, okay? So charge can create divergent field lines, but dipoles for magnetism can't, and you can't have magnetic monopoles. This equation says that in math, which is universal language, but a lot of people don't speak it. So this says there's 2 ways to make magnetic fields, right? So you can make electric fields with charge, and you can make electric fields with changing magnetic fields, okay? This equation contains both ways to make magnetic fields. You can make them with current, or you can make them with changing electric fields, okay? And more specifically, changing electric flux, but essentially the fields, right? So this is all of the equations that are considered Maxwell's equations, and in a sort of fundamental way, these are all the equations you need for this class, okay? Now, I mean, you have to know a lot of ways to get other stuff out of them, because even like Ohm's law comes from this, okay? Now, I know you guys aren't going to look at this and be like, Ohm's law just pops out at me now. But so you might want to also write that one down. But I'm just saying, from like a theoretical perspective, like all of the equations we use in this class pretty much come from these 3 equations, or 4, although that one's kind of useless. Okay. All right. So let's talk about field laws. We'll go through this. Okay. Gauss's law, that's electric fields. So basically, just to give you some visuals, if you have a point charge, what does the electric field look like? It just goes out like that. And you want to imagine it in 3 dimensions, because what do we have to put around it?
Sphere.
Yeah, well, this one would be a sphere, but any 3 dimension. It actually turns out, if you're not trying to solve the problem, theoretically any closed surface will work. It just would suck to have to do the math for something that wasn't a sphere. Okay, like if you get a computer to calculate it, you can pick any closed surface, you'll get the same answer. It's just that, remember, the surface integral over like a random shape that doesn't match the field vectors, it's going to be a huge pain in the ass, okay? But you can put a cube around this, it'll still give you, right, the right answer. It's just going to suck to do the integral. So we've strategized, when we use Gauss's law in practice, you want to pick strategic shapes to make the math easy, but that doesn't mean that other shapes don't work. It just means you don't want So here's our statement of Gauss's law for electric fields. And so if you put a negative charge in here, that just changes the sign of the flux, but you would also, and also therefore changes the sign of the charge. And so you just want to practically know how to use electric fields. And as we go through this, remember, Gauss's law will still be on the final, okay? So just reminding you. Of course, so let's say this is a loop of current. So you have current coming out and going in, it looks like this. Okay, what does the magnetic field look like? A bunch of other loops, okay? So if you enclose this, you'll notice everywhere a field line goes out, it also comes back in. So that means the net flux, right, that's going to be 0. Yes?
The Gaussian surface thing that you draw, why is there like a little dip over there on the left side?
It's just to show you that it's like an arbitrary
That it's not like a fundamental
shape. It
circle.
doesn't have to be like a sphere or anything. It just always works. From a mathematical perspective, if you can calculate it, any shape works. But that doesn't mean you want to do it. So, okay. Then we also talked about Faraday's law. That's like if we have these changing magnetic fields, you get this induced current, which means you have an induced electric field. Okay, so this says if you have a changing magnetic flux, meaning either the area or the field is changing, or the angle, right, then you can induce a changing electric field. And this negative sign says the induced field opposes the change.
So that's the conceptual negative side.
It's a conceptual negative, yes. I mean,
mathematically also, but more so because
it works
it's
mathematically. For our
direction.
purposes, consider it a conceptual negative, okay? Because, yeah, you have to really be a lot more rigorous about how you do your calculus to have the negative sign be meaningful and give you the right answer. It's a lot easier to check it with, like, physical stuff, okay? All right. Ampere's law says if you have a loop, okay, you also consider the surface of the loop. Anything that pierces that surface counts as the current going through it. You want this to be like this, all right? So here, you want to integrate around your loop, right? This loop is, all these little chunks are ds. You integrate the magnetic field around the loop. That's going to be equal to a constant times the current that goes through the loop. Okay? Now, Ampere's law, you'll notice we wrote this other version of it that has this extra term. We're going to talk about where that extra term comes from. Okay? Because clearly we haven't used it yet. We just mentioned that it exists. So, what Ampere's law does, if hopefully you remember it, although we haven't been tested on it, so maybe some of you have not really thought about it too much yet, okay? But you should. So Ampere's law sort of exploits symmetry by using a closed loop, okay? And that closed loop, anytime you have a closed loop, you can call that a bound surface, okay? So you just basically just color in the loop, and then that's the surface. But it turns out the surface isn't limited to, so for instance, the loop just gives you the boundaries of the surface, right? So let's say you have a circle. What sort of surfaces end on the circle? So what can you have?
A plane.
You can have a plane. That's the simplest one. That's one we usually use. But what else can you have?
A ring.
It still has to be like a surface area. But like you could have like a hemisphere, right? That would still be a surface that ends on the ring. Do you see what I mean? You could also have like a part of a cube that sort of like goes into a circle, right? You could have a cone coming off the circle. As long as the surface ends on the ring, that's still a surface bounded by the ring. Okay? So what I mean by this is, like, look, this is the one we normally use. Let's call this surface 1. But look, let's pull this out. It's not the only option, right? You could also have something that looks like this. Okay, that's still technically a surface that ends on this loop. Okay? And this is sort of like, there's some more formal math that goes with this, but we're not going into that. This is the conceptual version of the formal math. Okay? So it turns out, you can use these, and let's say we create this closed surface that these are both surfaces bound on the loop. Right, so everybody's on board with the idea that the loop can have any surface as long as it ends on the loop. Cool. So let's put a wire through this. Okay, so this wire comes in through this surface, goes out through that surface. Okay, so Ampere's law may be applied to this current, this I through, passing through any surface S that's bounded by this curve C. So here's surface 1, here's surface 2. And if it's closed, right, anything that comes in surface 1 has to go out surface 2. Okay, so let's try this out. All right, let's say you have some current in here, some current out here. What's the current through S1? I. What's the current through S2?
I.
What's the net current?
I. 0.
Well, I goes in, right?
Zero.
I goes out.
0.
So that's 0. Okay? And you're like, okay, well, what if you turn it so it goes out the same way it came in? Okay? Here's your current. What's the current through surface 1?
I.
You sure?
0.
Yeah. I minus I. 0. What's the current through surface 2?
0.
0. Okay, so there's a whole mathematical proof that shows, like, if you have a closed surface and you have something like this, the net current through the closed surface has to be 0. Okay, but I'm just showing you, as long as you define these shapes and these boundaries, this is what you get. Okay, say whatever goes through surface 1 has to also go through surface 2. All right, so let's add another situation. So what does this look like to you? That's a capacitor connected to a battery. Okay, so you can assume there's some current flowing through this system like this. Let's take our shape and throw it here. Okay? What's the current through S1?
I.
What's the current through S2?
0.
Yeah, we know there's no physical current that goes this way, right? Because we know what happens in between the gap between the capacitor plates is nothing. Okay, there's no charge that jumps across it. But we just said that if you have a closed surface, what goes in has to come out in terms of current. So is Ampere's law wrong, or are we just missing something?
Missing something.
Yeah, probably, because we know that we added this correction, okay? So we end up having this correction to Ampere's law. This is now called, then we rename it Ampere Maxwell Law. It's very anticlimactic. So, what do we know happens between the two plates of a capacitor? What do we have in there? Yeah, an electric field, okay? So, if we have an electric field between the plates of a capacitor, right? What's the electric field for a capacitor? This is a nice parallel plate capacitor.
V over D.
It's true. We're not going to use that for this, though. There's the sigma over epsilon naught. Okay. So we have a flux. So if we want to figure out the flux through this surface, and you can flip this around. That makes it a little bit easier. So you're just going through a flat surface. Okay. What's the flux through a closed surface? Right, what's the flux of this? So this is a constant electric field. Okay, so we want to calculate flux.
You want to just that?
And it's not closed, so we don't put the circle here. Okay, it's just let's just say it's a flat circle in between the plates. It could even be a square. It doesn't actually matter. Okay? So what's the flux? Well, let's say this surface is flat. Okay? What happens to the dot product?
It goes away.
It goes away because the area vector should point parallel to the electric field. Okay? And also we know if it's a constant electric field, we can pull the electric field out. This thing just becomes E times A. Alright? Now, the electric field for a capacitor, that's going to be sigma over epsilon naught. Sigma is what?
Surface charge density.
Surface charge density. So Q over A epsilon naught times A. You can cancel those out, so you just end up with Q over epsilon naught, which is not surprising, okay, because we know that the flux has to be equal to the charge enclosed, and we are enclosing some charge, all right? What this means is if you want to take the derivative of the flux, well, so we have charge, okay? This is the charge coming in. This relates somehow to what's happening in between the plates. We know there's not actually charge going across, but if you have charge, how do you get current?
Multiply by time. Or divide by time.
You take a time derivative.
That one.
So that's close. So this is flux, right? So let's take a derivative of both sides. Okay, so now you have d flux dt, so this is your electric flux, is equal to 1 over epsilon naught, some sort of current. Okay, but remember, this charge comes from the definition of the electric field between the plates, so it comes from the electric field. Okay, this means we have dq dt. This is some weird current from the field. Okay, but it does count as some current that's going through this other surface because we have a changing charge thing happening, at least in an abstract way. Okay, so this is sort of what the current version of the electric field passing through this surface means. And so if we solve for this current, we get epsilon naught d flux dt. Okay? Well, we know that Ampere's law says we have this whole thing, B dot ds is equal to mu naught I through. Well, now I is this current coming in, and also this other current that could happen, which is epsilon naught d phi dt. So you can have a physical current, that's the current that's I through, but also this other current, which we call the displacement current for whatever reason. Okay? And you can see, as you multiply this mu naught through, you get this. Okay? So this accounts for the fact that if you have something like a capacitor, if you have any electric field, even if you don't have moving charge, the changing electric field can count as a type of current. So this gives us something called the displacement current, and that means we have this corrected version of Ampere's law called the Ampere Maxwell Law. So that's the last piece that we hadn't really talked about in terms of these equations. Okay, so it turns out Ampere's law also includes changing electric fields. All right? So it means a magnetic field can be created either, and we talked about this before, but either by a current or by a changing electric field. Okay. All right. What do you notice about the sign of this, though?
Positive.
Yeah. So what does that mean? What did it mean when it was negative?
It was opposing.
What does positive mean?
Goes where it's probably.
Doesn't oppose, right? So it's going to go with whatever the change is. So let's try this out.
Folksy. It's dangerous.
Okay. Please discuss. We'll vote again.
I said C.
I said C.
But this one is just.
Okay,
you're going
that's
with
better.
the
So
magnetic field.
just like before, when we did Lenz's law, okay, you still want to sort of start out the same way because you have a magnetic, this time you have an electric field coming out of the page, okay, which means it's going to induce a magnetic field if it's changing. The way we did this before is we said, okay, this is coming out of the page, that means the current would go this way, which means if it's decreasing, it stays this way. If it's increasing, it goes the other way. All right? In this case, it's decreasing. You get just the opposite thing because, look, we have a different sign here. This was where Lenz's law came from, this negative sign. It always opposed the change. This one doesn't have a negative sign, so it doesn't oppose the change. It goes with change. Okay? So, just looking at this, it works a lot like the Lenz's law thing. You should still do right-hand rule. It just changes which direction you get at the end. So if this were a magnetic field inducing an electric field, the electric field would go this way. Because it's an electric field inducing a magnetic field goes the opposite way. And that's because of this sign difference. Okay? So the answer is going to be A. So, remember, but we were talking about how changing magnetic fields can induce electric fields, all right? It turns out changing electric fields can also induce magnetic fields. The only thing that's different is the direction, okay? And so this brings us to, this is the other picture. See, this is when he had hair on top of his head. I think that's just how people dressed then.
Yeah.
It's like, if you were in like college, you dressed like that, or you wore like a cape that made you look like a wizard. Yeah, like if you guys see, so like you know how like when you graduate you get to wear a cap and gown, like that comes from like a medieval tradition, and the style hasn't really changed very much. But if you go to like a lot of the schools in Europe, people wear those robes all the time. It's like Harry Potter probably isn't as like whimsical in Europe because that's just what school is like. So people have like their robes, and whenever they go to dinner, they just wear like it looks like everybody's graduating. Jeez. Yeah, but if you get a master's or a PhD in like England, you get the coolest regalia. Like your cap and gown is like way more awesome, and you get to look like Gandalf or well maybe more like Dumbledore. All the time, like whenever you see like the faculty from the UK, like everybody like from the US wears like dark blue or like black and like a cool hat, but from the UK they have like these silver and gold and red like things with streamers, and you look like it's almost worth going abroad to get your PhD just so you can wear that all the time.
Did all the travel shit, and then like
all right.
threw, like tons of crowds and like parade
I thought about it. Yeah, I just start showing up wearing that. Like, trying to take me seriously, guys. So what's this one called?
Electric flux.
This is one of Maxwell's equations.
It's
Gauss' law.
Yeah.
For what? Electricity or magnetic?
Electricity.
Yeah. So then we have Gauss's law for magnetic stuff. Okay, and this basically just says no magnetic monopoles. All right. Then we have this one. What's that one called?
Lenz's law.
Faraday, and then last but not least, Ampere's law. Well, Ampere Maxwell law.
Hybrid.
Okay. So I want to point out once again. I know I write these equations all the time, but I feel like it's important to like understand what they mean. It's like the most comprehensive theory we have in physics that like explains a whole bunch of stuff. So they're kind of exciting. Okay.
Yeah.
Maybe not to you. But that's okay.
Shiny.
So what this says is these are the source equations, okay? So anytime you see this current or you see Q, that is an electric or magnetic field created by a physical source, okay? So that means you have to have actual charges whether they're moving or not moving. So that comes from some actual object. These are just changing fields, okay? So you don't necessarily have to, at some point you have to have a source, but once you leave the source, you no longer have to have a source to keep the changing fields going, okay? They still keep traveling through vacuum or whatever, all right? And what that means is if you get rid of the sources, you can still have changing magnetic fields that induce electric fields and changing electric fields that induce magnetic fields, which means that if you start changing an electric field then you create a magnetic field, and then it creates an electric field, and then you create a magnetic field, and what do we call that?
Light.
Light. That's just light, okay? So that's why these equations are so important. We didn't really have much of an understanding of what light was. People did optics and all of that stuff over 1,000 years ago, and so they were sort of characterizing light, but we also didn't know that there was light outside of what we could see, okay? Because we only see in the visible range.
Makes sense.
But the electromagnetic spectrum goes all the way out, and wavelength, right? What's the wavelength of the light we can see?
Shit.
Fucking
I
remember.
don't remember.
It's like 300 nanometers, that's like purple, all the way up to like almost 800 nanometers, that's like red. So that's your Roy G. Biv. And that's a very small amount of the electromagnetic spectrum because you have wavelengths that are smaller than that. So once you get smaller than purple, right, what do you have? UV.
Oh,
Right.
yeah.
Ultraviolet.
Smaller than purple, like shorter wavelengths, higher frequency, right? That means more energy. So that's when things start getting crazy. So if you go in the violet range, then you get ultraviolet. What comes after that? X-rays. Then gamma radiation. Okay? If you go the other way, after red you get infrared, and then radio and microwaves. Okay? So those are long wavelengths. That means they are not super energetic. So when people talk about radiation, that's what really matters is what?
Wavelength.
The wavelength and the power, right? Well, the wavelength and the frequency go together because we have this really easy equation that comes up all the time that relates wave speed, and we haven't talked about waves, but wave speed is equal to wavelength times frequency, which makes sense, right? This is in meters. This is in 1/seconds. This gives you meters per second. Now, if you're dealing with light, what's the speed? The speed of light. That's the speed. So as long as you're in a vacuum. It gets complicated if you have to go through like water or glass or something else. But this says if we know the wavelength, we pretty much know the frequency because the speed of light is constant. Okay? So what matters when people talk about radiation is the wavelength and consequently the frequency, but those are pretty much the same thing. We also know, which we won't get into as much, that the energy of the individual photons, right, which is the fundamental unit of light, okay, is equal to some constant times the frequency. This is Planck's constant, but you don't need to know that for this class necessarily, okay? Which means that the frequency matters a lot, okay? So if someone says that radiation gives you cancer, you should say, which part of the spectrum are you talking about? Okay, so if your grandma's like, don't stand in front of the microwave, be like, shut up, Grandma, you don't know what you're talking about.
Yeah. No, it's my favorite. Shut up, Grandma.
You can say that nicer. But,
No.
so, just as a side note, at what part in the spectrum does just getting hit by light start giving you cancer?
UV.
UV, right? Somewhere in the
You
UV.
get skin cancer.
Why?
Melanoma.
Yeah, so it turns out that individual photons interact with individual electrons, right? So how do you get more energy in your photon? You have a higher frequency, okay? So the ones that we know start giving you cancer are the ones that can pull off an electron from your actual atoms, okay? That's called ionizing radiation, and that starts somewhere in the UV range,
It's fucking terrifying.
okay? So the sun has UV spectrum light, so you can get skin cancer. Yeah, that's a known mechanism. If you're getting hit with visible light, no. Okay, that's not going to give you any. There's no known mechanism.
Flashlight tag would have been scary.
The other thing is like the cancer is a slow process, so like you get hit with like ionizing radiation, like there's like a linear scale of the probability of getting cancer with radiation exposure.
Then, how does sunscreen combat that? Because isn't the main ingredient in sunscreen like zinc?
That's sun.
Yeah,
no.
it reflects the.
Reflects it?
It reflects the UV.
Oh, yeah.
Because remember, well, in this class we don't talk about it, but there's a difference between reflection and absorption, right? So different materials either reflect light or absorb it. And I mean, you can tell if things are being reflected in the visible range because you either see reflections or it's shiny. Yeah. So yeah, basically sunscreen either absorbs the UV before it gets absorbed into your skin, or it reflects the UV so that it never gets to your skin.
Cool.
Yeah. So actually, that's why the best way to protect yourself is just like a fucking shirt or a hat. Yeah. Because then if the UV can't penetrate it, then it's not going to give you cancer. Yeah. So just wear a shirt.
Or flannels.
Yeah. just wear your flannel to the beach. You'll never get skin cancer. You might be really sweaty though. But yeah, so anything above UV, and you can see like it gets more dangerous as you get to higher energy photons, so higher frequency, so X-rays, yes, right? Gamma radiation, definitely yes. Microwaves and like if somebody's like dumb people are always like, oh, your cell phone's gonna give you cancer, and if it does, it's not gonna be because of that mechanism, okay? There'd be something we don't know about, and we've had cell phones for a long time, so it's more likely that the battery will explode and burn your face, and that's something you should worry about, but getting brain cancer from talking on your cell phone, probably not.
Probably not. Probably.
Well, there's always things we don't know about, but I'm just gonna say, what we do know.
Oh yeah, because you keep it in your pocket.
That ionizing radiation has a mechanism to give you cancer. We haven't found any correlation or any reason to believe that if it doesn't ionize, it will give you cancer. Okay? Yeah. And so you know that basically, and why is ionizing? Why is pulling off electrons bad? So how though? Because it's more of a biology question.
It creates it in
changes your DNA, right? Or something.
It can, yes. So if you have, what electrons? What are we pulling the electrons off of most likely? What are you mostly made of?
Atoms.
Water.
Right? So you just ionize the water molecules in your body and then they're floating around. And normally that's not really a big deal. They'll probably find some other, well, here, if you count up all the protons and all the electrons in your body, what should you get?
Zero.
Yeah, it should be about the same, right? If you add up all the charge in your body, it should be about equal. So if you're knocking electrons off, now you have two charged particles. And so it's unlikely that they're going to run into other charged particles. But the thing about molecules is some of them are polar. So even if they have a neutral charge, sometimes, we know water molecules are polar. One side's more positive, one side's more negative. Okay? So now if you have just a charge floating around by itself, it can interact with these things that have sort of these charge distributions that are polar. Well, one of the main problems is if it ionizes another water molecule, we don't really care, right? Or if it just gets stuck to something else, we don't really care. So this is why it's a probability issue, because it depends on what that charged particle does after it's ionized. Most of the time it does nothing, but sometimes it interacts with your DNA, okay? DNA is very highly polar, so if you get a charged particle near it, okay, then you can rip pieces off of it. And it does have some self-repair techniques, so you may not still be, that's why it's a probability, right? You may not do any damage still, okay? But if it does disrupt your DNA in a way that can't be fixed, sometimes that causes DNA to over-replicate itself, and that's when you end up getting cancer. Did you have a question?
Yeah, is that the big deal about ionized water?
Oh my god.
That was the hardest eye roll I've
Yes!
ever heard.
The short answer.
I mean, there's like all these big articles. Oh my god, drink ionized water. I was like, water's water. Like,
so if you're not that smart and you hear
water.
this logic and you're like, well, all we have to do is put the other charge back in and then they'll cancel each other out. So then you end up drinking high pH water.
Yeah.
Yeah.
And then you're really basic. I know, I can talk about that joke. I came up with that in my 210 class, and I was really proud of it. So.
That's awesome.
But really, like, maybe that, but that's also dangerous because you're also introducing other charged molecules into your body. So it doesn't really change the equation because you're just as likely to make the water might be giving you cancer. I mean, but like, it's still a really low probability because if one molecule gets ionized, it's no big deal. It's just if this happens a lot, the probability starts, because it's a really low probability that something like this will give you cancer. It's not like every time an electron gets ripped off, now you have cancer, okay? Every time an electron rips off, you have like a 1 in a million chance of it, probably less, of it causing cancer. The problem is, the more radiation you expose yourself to, the higher, like the more that probability is significant. Right? Because if there's one incident and it's 1 in a zillion, who cares? But if you have a zillion incidents, then it's like a real problem, right? It's like when birth control is 99% effective, you're like, well then 1 out of 100 people is getting knocked up.
I think so. Yeah.
Okay, so
Someone's done that.
like that's how statistics works.
It sucks if you're that 1%.
Yes. So anyway, we got really on this
Shit
sidetracked by
happens.
this,
Yeah.
but where was I going with that?
Fuck cancer, fucking whole radiation.
So only certain parts of the spectrum give you cancer, definitely.
So,
Okay.
is that why they put a big lead fucking vest on you when you get an X-ray?
Yes. Also, if you know anything about biology, which I only sort of do, there's different. So first off, most of the time, where's your DNA?
The nucleus.
In the nucleus, right? And it's all like coiled up, but it's hard to get to. So it's pretty protected. When is the DNA easy for just like any random particle to run into?
In the mitochondria.
No.
When is it reconstructed?
No, that's, yeah, when it gets translated.
Yeah, when your cells are dividing,
Yeah.
okay? So there's certain cells that reproduce way more often than other cells. Those are the ones that are more vulnerable to that kind of stuff.
Like skin.
Like skin, right? You're constantly making new skin, so that's one of the. Because if you damage the replication of a cell that doesn't replicate that much, it's like well, it might not be that big of a deal. You'll get like one of these nice slow growing cancers that you can like treat, and it's no big deal.
Yeah.
It's when you get it in something that's like reproducing all the time, like and other also when you mess up the DNA of things that you use to reproduce, like so that's why you put the lead over your lap because that's where all your little guys are.
Isn't that also like they give you
or lady guys.
What's it called? I forgot what it's called.
The reproductive cells.
No, they give you when you have cancer. They give you a radiation injection, so that way when they take like your X-ray, they can see what cells are that have the cancer. And when that happens, you're not supposed to touch other people.
Yeah. So cancer treatment is interesting because we often use radiation to treat cancer, and this is like a tricky thing. It depends on the type of cancer.
Yeah.
But you're basically trying to kill the bad cells before you kill the good cells because it's a risk.
Risk versus reward.
Yeah.
It's like trying to put out fire.
It's like don't go get. Yeah.
Firemen do it all the time.
Yeah.
No, that's a thing, right? So you don't want to go. You don't want to get
use
an
up
X-ray
oxygen.
that you don't need. When do you usually get X-rays? Yeah, when the alternative to not getting the X-ray is worse.
Yeah.
Okay.
Like CTs
So,
and stuff.
like, if you get an X-ray, that's a very low risk of getting a secondary cancer, probably 20 or 30 years later. Okay. And a CT is a much higher dose than like a if you just like get an X-ray on your arm, like I think you get about like the same amount of radiation as like living in a brick house for a year or like flying around in an airplane for like a day. Okay, so you get exposed to radiation. So people like worry about radiation exposure, but you get exposed to radiation all the time.
Yeah.
Like right now, you're currently being exposed to ionizing radiation. There's just a baseline level that we're okay with, and that you have to be because there's just no way unless you just like.
Block
If you
out the
live
sun.
in a lead encased
Bubble
box, the
bubble.
lead will radiate some
Lead bubble.
radiation towards you. So it's always risk versus reward. And so most cancer treatment that involves radiation, yeah, you don't mind being exposed to it because the alternative is certain death, right? But yeah, other people who are healthy, who don't have a risk of getting, then you're giving them more risk of getting cancer.
Matthew just said like if you like he had a really young grandson, and they told him that if he like held his grandson for extended periods of time, he would sterilize him because he was so young. I was like, fuck.
Yeah. Well, this is a big problem in treating pediatric cancer. So if you're treating someone that's like 60 years old, right, and they have a cancer that might kill them, and you give them radiation, okay, there's not a lot of risk of creating a secondary cancer because the secondary cancer is not going to show up for 20, 30, 40 years, and they'll be dead anyway, okay? So this is how we do these assessments. But in pediatric cancers, if you're treating someone that's 5, you're hoping they're going to be around in 20, 30, 40 years. So like a lot of the lymphoma treatments, a lot of the kids get a different kind of cancer. Usually it's a fairly benign form, but they'll get them as an adult because the treatment itself causes a secondary cancer. Now, you're like, well, then don't get the treatment. But it's like, well, no, then you'd only live to be 6.
And you die.
You have the luxury of growing up to get a second cancer, okay? So it's always risk versus, you always have to weigh different variables and make decisions based on those variables. It's not, everything is not black and white. That's why it's important to understand what a spectrum is, okay? Some things are slightly better, some things are way better. It's not yes or no, good or bad, okay? The world is very fucking complicated.
It's very gray.
Yeah. Okay, so anyway, after that big aside, good thing we have extra time, Maxwell's equations, the consequence is light. Yay! So let there be light. All right, it's very pretty. Where'd it go? Oh, there it is.
Oh, there.
And here, this is the, remember I was talking about the differential form of these equations, okay? See, this is Gauss's law, written in different units in the differential form. You don't have to remember this, but this is just to show you what it looks like once you know what vector calculus is. Okay, so this is the divergence, right? Divergence. This is the curl, but you can still see this is looking at the flux if you have a charge enclosed. Okay, this is looking at the changing magnetic field creating an electric field. This is if the flux through a closed surface for a magnetic field is always 0. Okay? When you do divergence, this is inherently saying this is a closed surface. How many of you have done divergence?
In calculus?
In calculus.
Yes.
Yeah. So divergence theorem looks like this is equal to this. That's it. Okay? That's why you need to know divergence theorem, because then you can go back and forth between these two forms. All right?
Yes.